Okay, so now for our second AP review topic, we're going to look at Newton's laws. Wow, that's bad handwriting. Let's see if I can do better than that. So, yeah. There we go. Newton's laws of motion. And just hit a few highlights. The first law is often called the law of inertia. And this law is that an object will stay at constant velocity or will maintain a constant velocity unless acted on by an outside force. So this outside force means outside the system, an object that is not part of your control group or your system of your studying. And so what we need to remember first of all is that inertia is not a force. Inertia is a property of matter, of mass. It is not a force. Not a force. Secondly, this maintain a constant velocity can be zero. So it can be zero, or it can be some value that is, positive or negative. So we say constant velocity, we're talking about objects that are at rest, will stay at rest, or if they're in motion at some speed, they'll stay in motion in the same speed, same direction. So last but not least, constant velocity means the same speed in the same direction. So you only have constant velocity if you move along a linear path, straight line, and you stay moving in the same direction the whole time. So same speed, same direction. Okay, so that's your first law. The second law is the one we usually write as an equation, and it is acceleration is directly proportional to force, directly proportional to force, and inversely proportional to mass. In other words, force over mass equals acceleration. But usually the way we write it is the net force is equal to mass times equation, mass acceleration. So we tend to like the second format better because most of us don't like to write quotients. We prefer to write products. We like to see things multiplied together rather than divided. So an object's outside force, this net force, remember, means the sum of the forces. Read this as the extra unbalanced amount of force it's not the balanced part, it's not all the forces, it's the unbalanced amount of force that causes the object to accelerate. And the larger the mass, of course, the harder you have to push, or the larger the mass, the less acceleration you get out. The last law, of course, is the one that says forces come in pairs. So the third law is forces come in pairs. And we call those forces action-reaction pairs. And the key thing to remember here is you have to have one force on each object. So for example, right now in front of me I have a Diet Mountain Dew sitting on the table. Got a Mountain Dew sitting here. And there's a force here because forces are really just interactions between two objects. So there's no such thing as an isolated force. You can't have a force that doesn't act, that doesn't come as a pair. So in this case, the free body diagram for the can has force due to gravity down and force normal up. Now, just to make this really clear, this is not an action-reaction pair because they're on both on the same object. Do they cancel out? Yes, they add up to 0. There is no net force. But that does not make them action-reaction. Action-reaction pairs, one has to be on the can and one has to be on the table. So if I was to do the action-reaction pair for the table and the can, here's what it would look like. The table has acting on it a force normal from the can. The can has a force normal from the table. The table also has a force due to gravity, and it has a force normal from the floor. So the action-reaction pairs here are this one on the table and this one on the can. You must have one force on each object. The forces must be equal in size, so same size, same length of arrow, and they point in opposite directions. So that is how the third law works. Now, we've done a lot of time working on problems on this, so I'm going to work a couple of more problems, because we always do. But if you want to stop and pause here before I give you the explanations, feel free. So the problem we're going to work on number 57 is going to be number 57. Start with number 57 over here. So if you want to read it, go ahead. I am going to draw the free body diagrams and then I will start explaining. Okay, and like I said, feel free to pause anywhere you need to. So let's show this one. Since this is a bigger object, it's going to have larger force of gravity. This is the 9 kilogram block. And it has a force tension. 1 is to the right, and 24 newtons is to the left. So I should try to make these two, this is my action-reaction pair. Hang on just a second. Pull that, make that just a tinge longer. So these two are an action-reaction pair. So if anybody says to you, I can exert a force on myself, that is simply not true. You can't apply one force. If you apply one force, you apply two. And if I apply a force on myself, I can't, then there must be another force being applied on something else. So if I, the object, can't push on myself. Yes, I can hold my hands, yes, I can push my knees down, but those actions are when you start to consider the body instead of being a single object. The body is made up of hands and feet and toes and noses and such. So I can't take a force. If I look at my whole body as the object, I can't apply a force on myself. Any more than the 3 kilogram block can apply a force on itself. The object is the object. So, how in the world are we going to figure this out? They say 24 Newton horizontal force pulls on the larger box. With what force does the larger box pull on the smaller box? Well, what I'd like to be able to do here is I'd like to just go, okay, force tension 1, this is my unbalanced force, is equal to mass of block 1 times acceleration of block 1. And then I just know, because I could fill in the 3 here, but here's the problem. I don't know this. I don't know this acceleration. And since I don't know this acceleration, and I don't know this, so I've got a question mark here and I've got a question mark here, I'm going to have to resort to doing something else. So here's what I'm going to do in this scenario. They tell us that it's a frictionless surface, so on this block, the sum of the forces, the net, the unbalanced amount that is horizontal, is going to cause the 9 kilogram block to accelerate. Whoops. 9, not S. So we have our forces that we're going to add up. What forces do we add up? We're going to add up 24 to the right minus force and tension 1, the rope that pulls the second block, is going to work against that force, so we give it a negative sign, equals the mass of the block, which is 9, and the acceleration of the block, which I don't know. Okay? So you say, now, Miss Wilson, I don't know how to answer that. Because, once again, I don't know two things. So what could I do? Well, can I call this acceleration, is it the same value as that one? And the answer there is yes. These two are equal to each other because both blocks move together. Both blocks are connected. So that if one accelerates, the other one has to also. So here's what I've got. Force tension 1 equals MA, and 24 minus force tension 1 equals 9A. So here I go. 24 minus 3A. So these are equivalent. So 24 minus 3A, boom, equals 9A. So 24 equals 12A, so A equals 2 meters per second squared. Now I can come back up here and find what I wanted. Force tension 1 is 6 newtons. So block A pulls, or block 3 kilogram block pulls backwards on the 9 kilogram block, and the 9 kilogram block pulls forwards on the 3 kilogram block. So my answer here is letter B. Hope you guys got that one. That's a pretty straightforward problem, but you know, this is physics, and physics is often very difficult. So, new page. Let's look at another one. Get over here. So, I'm going to look at, this is going to be problem number, let's see what I got there. You'll notice it's question number 71, so we're going to do number 71. Just to refresh how the angles work. So they tell us, pause if you want to, right here, a box with mass 50 kilograms dragged across the floor by a rope, which makes an angle of 30 with the horizontal. Okay, just like the picture shows. Which of the following would be the closest to the coefficient of kinetic friction between the box and the floor if a 250 Newton force is applied to move the crate at a constant speed? Okay, so here's what we know. Start with our free body diagram. Here's our graph. So we have a free body diagram of, this is 250, and the angle is 30 degrees. I also have a force due to gravity that is straight down. So here's force number 1, that's a tension. And then I also have friction, and friction has to oppose our motion. So here's going to be my force of friction. So when I work this problem, what I've got to figure out is what force do I need. So here we go. We've got to get the force that will balance. So I am looking for, I know that this leg of that triangle, so if I think of this as a triangle that I pull out, where the hypotenuse is 250, and this is 30, this leg right here, the horizontal leg of tension, is going to be balanced by force gravity, or excuse me, force friction. So force friction equals force X, and force X is going to be found like so. X over 250 equals the cosine of 30. So X equals 250 cosines of 30. So in this case, let's pull out our cute friend calculator. Make sure we're in degrees. 250 times the 30's cosine. So 250 times cosine of 30 equals 216.5 newtons. And then they asked me what the coefficient of friction is. Okay, so coefficient of friction is going to work with, we need to know what the force normal is. Here's my force normal. It's going to be the y component. So force normal is equal to Fy of the tension force, the part of the tension force that goes upwards. So to get that, I'm going to use X over 250 equals the sine of 30. Whoops, sorry, that's a y. We're doing vertical. Y over 230, y over 250 equals sine of 30. Wow, talking. So 250 times the sine of 30. Sine of 30 is 1/2, so this is 125 newtons. So now we have the two pieces we need. We're going to use the formula off the equation sheet. Force of friction is mu times force normal. So force of friction, 216.5 equals mu times 125. So mu equals, once again, handy calculator, 216.5 divided by 125 is 1.732. And let's see where we've got. Hang on just a second. Let me check my math. 30 sine times 250 equals, oh, you know what? Just dawned on me. I was fixing to remind you to not make this mistake, and then I made the mistake. Here's what the mistake is. All of this is right. Y has to balance force gravity. That was careless of me. So Y equals the force of gravity, because this leg up has to balance that leg down. They're the only vertical forces in the problem. So that one would be 50 times 10. Whoops, 10. So the Y leg, no, that can't be right either. 50 kilograms, 250 newtons. The normal force, so here's our, okay. Wow. Please forgive me. What forces do we have? Force tension up, force normal up. I didn't draw it, that's what the problem is. My picture's wrong. Force normal up. So force normal, and I was going to remind you to not make this mistake, and then of course I make the mistake. So force normal and force tension add together to give me the force due to gravity. They have to balance gravity. So we know that gravity is 50 times 10. We don't know force normal, but we do know that force tension is 125, and that comes from y over 250 equals sine of 30. So y equals 250 times 1/2. So y equals 125. So force normal minus 125 equals 500. So let this be a lesson to you that even Miss Wilson has to pay attention and draw the right picture. I completely forgot to put in force normal. I'm sure you guys would not have done that. So now I find force normal. Ooh, not yellow. Yellow's not a good color for that. So force normal, I don't know. But if I take away 125, I get 500. So my force normal must be, plus 500 minus 125. So force normal is 375 newtons. Now I'm ready to come over here, and I have 216.5 over 375. So our coefficient of friction is about 2/3, looks like. So the one that is closest to that, 216.5 divided by 375 is 0.58 newtons, is what I get. And they have a choice of 0.5. So D is the correct answer. Now, let me back up to the beginning of this problem. What's the most common mistake? Well, I just made it for you. Made it twice, in fact. You have to draw a correct free body diagram, because if you don't show all your forces, you're going to make mistakes when you try to combine them. So here, I have two upward forces. I have force normal is upward, and there's a force right here that's upward. And so those two forces have to work together, thus the plus sign over here. They have to add up to the same thing as the weight. And once we know that, then we can just ratio force normal with, force friction, and then we'll have the correct answer. So that problem's, these two were a little bit longer problems, but you might see this in a free response now, or at least have you talk about it. They might ask you if the force in the tension in the rope is the same as the gravity force. No, it's not. It's littler because the surface holds it up and the tension force holds it up. All right, so last problem on this, and I may have shown you this one before, but just in case I haven't, I'm going to put a new page in, and we're going to look at this one. All right, so here we go. Pause if you want to, then you can come back and watch. Okay, so in case 1, I have the big block M has these forces. Force normal, force gravity on the big block, force tension. Case 2, I just have force tension, force normal, and force gravity. And you may say, Miss Wilson, those two free body diagrams are exactly the same. Yes, for the block on the table doesn't know if it's connected to another object or somebody's just pulling on the rope. Okay? So those would be the free body diagrams. Now, what's the free body diagram for the hanging object? Give you a second. Hanging object is going to be force due to gravity and force tension. I'm going to make force gravity noticeably longer because it says the block is released from rest, so it's going to start to fall. There's no friction that would cause the big block, the block of mass M to stick on the table. So here's our two answers for the first part. Now they're going to ask you argumentation. Angela and Dominique are observing this demonstration, and note that the block accelerates in both cases. However, the block reaches the right edge of the table in less time in case 2, even though the force on the string in this case is the same as the weight. This occurs because there's a different amount of tension in each case. Why does the block reach the end faster in time 2 than in time 1? What is going on with the tension is really what this question is. In case 2, let's start with case 1. In case 1, the weight of the hanging mass causes both masses to move, or both masses to accelerate. So there is more mass in the system than in case 2. Since acceleration depends on mass, less mass implies greater acceleration. And you can abbreviate it like that, and then you can say force equals ma. So there's your second law. So there's a different tension because in the first case, the hanging block has to pull itself. Well, it doesn't pull itself, gravity pulls it, and it moves as well as the other block. So you have two masses in the problem. In case 2, even though you apply the same amount of force on the string, since you only have to move one mass, less mass means a larger acceleration. They are inversely proportional. Okay? Now, part 2 says, let the system in case 2 consist only of the block on the table. Explain how Newton's law, when applied to these two systems, predicts that the block in case 2 reaches the end of the mass or end of the table in less time. So here's part C. So here's what we're going to say in part C. Newton's second law is mass is force times acceleration. So acceleration depends on net force divided by mass. In case 1, m equals little m, equals capital M plus 10. So A equals 98 newtons over m plus 10. But in case 2, acceleration equals 98 over m, so there is a smaller denominator which leads to a greater acceleration value. So that's why it accelerates more. We got to finish this up. Since it has a greater acceleration, it reaches the end of the table faster. In case 2. And really, you'll notice Miss Wilson is now going to go, okay, I've got that explained, I feel good about it, but here's what we've got to do. You notice I have two pronouns. So I'm going to go back through this and check it real quick. Ooh, pronouns. Since the system has a greater acceleration, the block reaches the end of the table faster in case 2. So I'm going to make sure I don't have any pronouns is my other check. So when you're explaining, you literally can show the math and then just say what it says. Okay? So that's where we're going to stop on this one, and we'll catch you on the next review session.